Hello! In this video, let's talk about the centroid, namely the center of mass. And let me give you guys the one-dimensional situation first, so that we can use that to understand the second-dimensional situation, and also show you guys the integration formulas at the end, alright? So check this out. Suppose you go to a park and you want to play seesaw with somebody, and let's say here is the seesaw bar. And assuming that this right here is just 4 meters long. But the deal is that you can actually move the center wherever you want to. But the problem is that, well, you and the other person, you guys are just going to be sitting at the end. Well, let's say we have this guy right here. He's pretty massive and he is 100 kilogram, all right? And let's say we have a more skinny person right here, and this is only 60 kilogram. And the question for you guys is that, where can you put the center or the thing, right? Right here, so that you can keep this balance. Well, it's not possible. What do you guys think? It's definitely possible. You just have to place that thing, right, the center, to the right place. And we know, because this guy is heavier, so we should definitely place the center slightly toward this guy, right? It's not really right in the middle because we have to care about his mass and all that stuff, right? So here is the deal. This right here is kind of like the weighted average kind of thing. This right here will be balanced. I will just write this down right here for you guys. Will be balanced if the following happens. First, you care about the distance from here to here. I will just call that to be D1. And then you will also know the distance from here to here. I will call that to be D2. This right here, I will call this to be M1 for mass. And I'll call this to be M2. And you can also talk about the weight, but doesn't really matter as long as you're consistent, it's okay. But D1 and M1. Well, this right here is going to be balanced if D1 times M1, that's equal to D2 times M2, right? And what does D1 times M1 mean? Well, this right here is what we call the, not the torque. What's that called? The tendency of rotate, I forgot. Oh my god, I used to know this. Moment, there we go. The moment that you forget about what the moment is representing. Yeah, caught on camera. But anyway, here's the idea. Distance, you can just imagine that I'm trying to hold out a calculator like this, right? So, I can hold out this calculator for a pretty long time because this calculator is not so heavy, right? But imagine if my arm is like super long, then that will be tougher because I have a tendency to rotate. Yeah, and you see, this is what we mean by tendency to rotate. Because you are not just going to drop the calculator. You are going to, see, like this, right? This is rotation, like that. If I am trying to hold up this guy, it's going to be harder for me because this guy is heavier, right? And you see, if the moment on the left-hand side is equal to the moment on the right-hand side, you can keep it balanced. That's the idea. Pretty good, I would say. All right. So now, based on this, we can of course compute it pretty easily. Alright, D1, we don't know. So let's go ahead and do that. I will just keep it as D1. M1 is 100, so we will multiply, and that's equal to D2. Well, don't bother with D2, because we know the whole thing is 4, and this is D1 already. In the end, I just have to tell you where to place the triangle, right? So we can say D2 is the same as 4 minus D1. And that's much better because we can just set out the equation with one variable. Alright, so this right here is just 4 minus D1 and then times M2, which is 60. And then of course, let's just solve this real quick. This is 100 D1 equals 240 minus 60 D1. And then we just get 160 D1 equals 240. Divide the 160 on both sides, you actually get 1.5. So what this is saying is that we should definitely place the triangle 1.5 meters away from the guy who is 100 kilogram. So we'll just say this right here is 1.5 meters away from this guy. And if you do that, you can actually keep this balance, right? That's pretty good. So hopefully this right here is okay, but in order for us to really understand the second dimensional situation, I will have to utilize this right here and change it to another look, right? But first of all, before we do that, imagine if I have another guy right here. Maybe because this guy in blue, he's like thinking that guy is too massive, so he's going to help you out. If I put down the guy in blue right here, what should we do to our equation here? How should we make adjustment? Well, again, you have to remember the idea of the moment. But this time, we have two guys on the right hand side. You have to care about the distance from here to here. Let's say these three, and let's say this is M3. You will just have to go ahead and add these 3 times M3. And this will be the total moment, right? Keep that in mind. Now, again, let's go back to this one more time, but another look. So, here we go. Let me just draw this guy again. Let's say this is the guy who is 100 kilogram, and then he is right here. And this is still 4 meters, so it's about like this. And what's still right here? This is 60 kilogram. And suppose these are the only things that we know. And again, the same question, we want to find out where we can place the center underneath this so we can actually keep this balance. Well, here is the deal. For the one-dimensional situation, we are going to set out an x-axis. So I'm just going to say this right here is my x-axis. Right? And in math, in physics, or in real-life situations, you have to learn how to set up your reference frame in order to continue with the math. So that's the idea. Once you set up the x-axis, you have to tell me where the zero is. And perhaps it's just easier to say, let's say, at this big guy right here, zero is right here. Well, this is definitely okay. But if you set up your x-axis right here and you say the zero is right here, is that possible? The truth is, yes, it is still possible, because in the end, we care about knowing where to place the triangle, and it's not to know like where the x value is. So that's the big difference. And let me just demonstrate the idea. Again, this might be slightly confusing, but I just want to make a point. I said I can put a zero right there, but I don't want to. I just want to make a point. So let's say I place the zero right here. And this right here is 2 away from the big guy, right? So that's what we have. And because from here to here is 4, so what does that mean right here? You just do 2 plus 4, which is 6. So now you see, we know the positions on the x-axis of this guy and that guy according to this x-axis. All right? If you have a different x-axis, your x values might be different, but it's okay. In the end, the final answer will be okay. Now, this is how we are going to do it. I still do not know where to place the triangle, but I do know that it will look something like this, right? Well, right here, we'll call this x-coordinate with x bar. X bar is the x value of the center of mass, all right? And it's right there. Well, let's see how we can solve that right here. Have a look. Knowing this right here, we have the following. You see, based on this picture, I will need to know the distance from here to here, right? So let me just show you. Just like that. But this time, you really have to do the math with this picture. What's the distance from here to here? It's always right minus left, the big number minus the small number. So this distance is x bar minus 2, right? Great. Well, similarly, what's the distance from here to here? It will be 6 minus x bar. So just write down 6 minus x bar, right? Then we can go ahead and set that up. But I'm not going to put on the 160 yet. I'm just going to do the following. Again, distance times the mass. So for this guy right here, you will see that I will have to have the distance being x bar minus 2. And then I will multiply this by, I will say m1 for now. And that we will have to make it equal to the distance, which is 6 minus x bar, and then I will have to multiply this by m2, like that. Now, I would like to show you guys the formula for x bar. So let me just multiply things out and all that. So if we do that, this is x bar times m1, and then minus 2m1, and that's equal to this times this, which is 6m2, and then we have minus x bar m2, like this. I'm going to move this to the other side, and both of them have x bar, so I will factor that out as well. So we have m1 plus m2 times x bar, and that's equal to, I will move this to the other side. So I will put this down first. So we have 2m1 plus 6m2, like that. In the end, you can see that x bar is just nicely equal to 2m1 plus 6m2 divided by m1 plus m2, like this. All right? Well, do we know m1, m2? Of course we do. We can just plug in the m1 and m2 right now. You will see that x bar, if you would plug in 2 times m1, which is 100, and then you add it with 6 times m2, which is 60, and then you divide it by m1, m2, so it's 100 plus 60. Now, question for you. What's the answer right here? The answer is not 1.5. Rather, the answer right here is actually 3.5. Why? Because we set the 0 to be right here. X bar, it will be 3.5. But if you tell me to put 3.5 meters away from the 0, this is equivalent to say, put the triangle right here 1.5 away from the big guy. Same answer at the end, right? So this right here is it. Again, it depends on what you and where you set up the x coordinate system and all that stuff. But please pay attention to this right here. This is the main deal. Have a look. All we have to do is pretty much the total moment divided by the total mass. Because this right here is the distance. Distance times the mass. And again, this is the distance times the mass. You see, what's m1? This guy's mass. 2 is the distance from here to here. Likewise, 6 is the distance from here to here. And then you multiply by m2. So moment plus another moment, that's the total moment. And you divide it by m1 plus m2, which is the total mass, right? So I will actually write that down because that's more important than just this question. This right here, I will just remind you guys, this is the total moment. I will put this down right here. All right, let's say total moment. Right, total moment about 0 right here. And then on the bottom here is the total mass. And you can extend this concept to more people if you like. If you have more people right here, you can just continue adding them. All you have to do is just plus the position or the distance of that guy times its mass. And then on the bottom, just make sure you add more and more mass. So that's pretty much the idea if you have more people being involved in this seesaw. So that's pretty much it for the first situation. Namely the first dimensional situation. Now, let's take a look at the second situation, which is the second dimensional situation. So, here's a question for you guys. Suppose I give you guys a rectangle like that. Let me just make it slightly bigger. Alright, two-dimensional situation. Let's say we have this rectangle. My question for you guys is that where can you put your finger and you can make this thing boundless? Well, the answer to that is just literally right in the middle, right? And if you do that real quick, you can actually just keep that balance. See, like this. And you can do this geometrically as you like. All you have to do is the following. Draw the diagonal from here to here. Likewise, do another one right here. And you will guarantee to find the middle, namely the center of mass, namely the centroid. Well, rectangle, square, they are straightforward to do. How about circle? This right here, again, is just literally right in the middle. And one way to do it is you can just fold into half and then fold into half where they cross each other. That's pretty much it. So if you kind of just fold this into half and then just do another diagonal anywhere, sorry, diameter technically, then you will be able to find the middle. How about if you have a triangle? We have no diagonal or diameter anymore. How can we do this? One way to do it is you can cut a triangle off and then you can just try to play around with it like that if you would like, all right? So yeah, don't know if I can, hey, I succeed. Look at that. Or you can do the following. Go to this side, measure the middle, all right? So let's say it's right here. And then go to this side and measure the middle. Let's say it's right here. Go to this side and measure the middle. And what you do is connect from here to here, connect from here to here, connect from here to here. This is called the median. And the point of intersections, the point of intersection of the medians is going to be the center of mass. Again, you can place your finger right here and can balance that triangle. Great. Now, rectangle, perhaps it's the easier one, right? But what if I cut off a little corner? Then in that case, it will look like something like this. In this case, what do we do? Well, too bad. I don't know. Because I don't know. Right? This becomes much more difficult. So let me just put that down right here for you guys, right here, right? And I will give you guys some actual numbers so that we can actually do the computation right here. So question, find the centroid of the following. So I'll just put that down. I will have like this, like this, like this, and then like this. Yeah, that's which way? Let's do it this way. Yeah, I have to do that like that. And let's say, all right. So let me give you guys some actual numbers. So suppose from here to here is 4 units, and from here to here is 10 units, all right? And I cut off a square right here. So I'll say this is 2 and 2. And let's say this is also a square, right? Just excuse my picture for that. Anyway, where is the centroid? This is much more difficult, right? This is how we are going to do it. You're going to break this down into the shapes that you know. It's either this, this, or that. Those are the shapes that you can find them easily. There is a nice formula to find out the centroid without doing this geometrically, but maybe that will be for another video. Anyway, what I will do is I'm just going to cut this into 2 parts. This part and that part. So we have 2 rectangles. And again, per our discussion earlier, we are going to also set up a coordinate system or the reference frame. At this time, I'm not going to do anything crazy. I'm just going to put down the bottom right here to be the x-axis. And I'm going to put down this right here to be our y-axis. Right? So that should be pretty fair. Now, based on all this, can we find out the coordinate of the centroid for the bottom one and also the centroid for the top one? Yes, and let's look at them individually. So if you see right here, so again, this right here is just the bottom portion, and let's focus on this before I put down another one. From here to here is 4. From here to here, because I cut off 2, so that means this right here would be just 8. So that means the centroid, it will be just halfway here and halfway here. So we have somewhere here, and the coordinate is 2, 4. Okay, 2, 4. And again, it's all based on x-axis being right here and the y-axis being right here. And we are good, all right? Not so bad. Now, if we look at that, which is just a small portion right here, well, we cut off 2 right here from 4. So that means from here to here is 2, right? And then from here to here is 2, as we said. So that means the center, or the centroid, is just right in the middle. You go from here to here, which is just 1 unit, half of 2. So you see that's right away, x coordinate is 1. And then from here to here, it's also going up by 1. But you have to go up from the bottom all the way to here. So it's 8 plus 1, which is 9. Great. So we have the coordinate of the centroids of this and that individually. Now, we are going to utilize this idea right here. This is how we are going to do it. First of all though, for the two-dimensional situation, not only you have to find out the x bar, but you also have to find out the y bar, because it's two-dimensional. But have a look, x bar, based on this idea, but again, this is a two-dimensional situation, we have to change it a little bit. Instead of talking about distance times mass, what we have to do is distance times area. X bar, you look at the x distance horizontally, the horizontal distance, right? So have a look. I will have to compute the distance from here to here, which is 2. So I will put down the distance, which is 2, times the area of this rectangle. The area is just 4 times 8, which is 32. So let me just put down 32, right? And then we are going to add, again, we are still talking about the x bar. The next thing is I will have to add the distance from here to here, which is just 1. Again, the horizontal distance, all right? Well, it's just 1 times the area right here, and that's 2 times 2, which is 4, like this. So you can see that I used the area to replace the weight that we had earlier. And then we are going to divide it by, instead of the total mass, well, the total weight, well, mass actually. Right here, we have to divide it by the total area. So I will just put down 32, the area right here, plus 4, the area right there. And now we can just work this out, and I'll leave that to you guys. You guys will end up with 17 over 9. And that's a little bit less than 2, right? So it's like, you know, right here somewhere. Now, yes, I make a mistake. That's why I erase this and make a cut anyway. Now we have to figure out y bar. So pay attention to this one. So we have y bar, but we are still going to use the same concept. Have a look. Again, distance times area plus distance times area, right? So first, let's look at the big one right here. What's the distance? Again, the distance this time though is the vertical distance. So we have to go from here to here. The vertical distance from here to the centroid. And because from here to here is 8, halfway is just 4. So the distance right here is 4. So we put down 4 times this area, which is 32. And then we add the distance from here to here. So you see, from here to here is 8 already. Go up 1 more. Altogether, we have 9. So we have to add 9 times the area of this, which is 2 times 2, which is 4. And then divide it by the total area, which is 32 plus 4. And in the end, you end up with 41 over 9 after the computation and all that. So this right here is a little bit less, well, it's about halfway between 4 and 5. So you can see that it's somewhere right here, right? A little bit less than 2 for the x, and then a little bit more than 4 and something. So it's about right here. That's the centroid if you cut this little part off. So that's pretty cool, huh? All right, so I'll just tell you guys the answer. When you answer this, you just write down 17 over 9, comma, 41 over 9. And then with that, you are done, right? But let me put this down into the summation form, because that's going to really help us with the integration formula. So the biggest note that you have to get from this example is that x bar is equal to, you see, we are adding stuff up. So use the summation. So we will have the sigma. But Don't worry, this is not the infinite series. This is just the easy way for us to add things up. You will also see this notation in stats a lot as well. Alright, what we do is usually we just put on I depending on how many things that we have. And then what we can say is, well, we have to have the distance. So we just put down xi. That means the distance of the first one that you are doing, and then the second one and the third one, depending on however many you have. And then you multiply by AI, area of whatever that we are talking about. And then divided by the sum of whatever, all the things that we have, of all the area. So we just have AI like this. And again, xi means the horizontal distance. Similarly, we can also put on y bar, which is just going to be the summation over I. And we will write it as the vertical distance, which is just yi, and then we multiply by ai. And then we divide it by the sum over all the rectangles, all the shapes that we have. And then, again, it's just all the area, like that, which is pretty good. And again, hopefully this example is reasonable. You guys can see that you cut this part off, you will just have to move the centroid to here, right? A little bit like that. So hopefully this is pretty believable. Okay, here's the best part. We are going to find the centroid with some weird shapes. And yes, we will have to use integrations. So have a look. Suppose I give you a shape, let's look like this, all right? Well, it's a typical picture for the area under the curve, right? Yes. So you see, this right here, I will call this to be y equals f of x, and then I will do the usual setup. Namely, I will just put down the x-axis right here, and then let me say the y-axis is right here. Well, let's see how we can do that. How do we do the area of this kind of things? We draw rectangles. Yes, we do the same thing right here. We love rectangles. So have a look. First, I'm just going to draw the rectangle right here. So I'll put this down in black, like this. And it doesn't really matter if it's a left-hand rectangle or the right-hand rectangle, does not matter, all right? Because this is meant to be really, really small. And then we're going to add up everybody from A to B. All right, let's do some labeling. First, from here to here, it's just a small change in the x values. So I will denote that by dx, right? The small change in the x values. And then the distance from here to here is just the vertical distance, namely y. Perfect. And now, if you just focus on this rectangle, which is again meant to be really small, I just have to draw it big so we can see it. It's a rectangle anyway though. Where is the centroid? Right in the middle, right? So I will just put a point right here, right in the middle. Halfway, technically. Okay, let's figure out a formula for x bar. Well, here is the deal. It says we have to do the distance times the area, right? From what we did earlier. So we have to do that as well. For the x bar, we look for the horizontal distance. And the xi is just meant to be this rectangle. You don't have to put on the xi right here. I will just give you guys the final result. So the horizontal distance is just from here to here. We will denote that by x. And x changes depending on where we go, right? So first we have x. That's for the distance right here. Next, we need to get the area of this rectangle. Well, the area of this rectangle, you see the base is dx, the height is y, so it's just this times that. Just like that, right? And you see, here we have the summation, and remember, summation is for finite amount. We use integration when we have infinitely many of these rectangles. Again, this is meant to be so small, and then you are just going to add up everybody. So for this, we integrate it from A to B as usual, like that. So that's what we have. And then don't forget, we still have to divide it by the total area. And you see, we just have to divide it by integral from A to B of y dx, like this. That's all. right? That's it. So here's the formula. However, as always, y is not allowed in the x world, so we just have to put the f of x right here. That's pretty much it. Another thing is that though, for this, it's just the area from here to here. So I'm just going to call that to be A equals the area from A to B. And we have to integrate the function dx. This is how the formula is usually presented. So remember this. We have 1 over A, again 1 over the area. And then we have the integral from A to B. X is just x, so we'll just keep that. And then for the y, again you put down f of x. And then we have the dx at the end. Phew, just like that. Now, let's take a look at the y bar. So we are looking at this right here. So I'll put this down in blue. Have a look. First, let's talk about the distance. And this one is the vertical distance. This, we just have to go from here to here, namely the centroid of the rectangle that we are looking at. Right, just like the one that we did earlier. Well, what's this then? You see? The whole thing is y, but the vertical distance is just halfway. So from here to here, it's just technically 1/2 y. So I'll put that down right here. So that's the distance. I will put that down for you guys right here. And then what's next? The area of this small rectangle. So I will just pretty much put that down, namely y times dx. Are we done? Pretty much, because the rest is just the integral from A to B, and then you divide it by, again, the total area, so it's just the integral from A to B of y dx, like this. Yes, finally, I'll tell you, y bar formula is just 1 over A times the integral from A to B. And usually we keep the 1/2 inside because we want to have the 1 over A, both of them like on the outside. So here, what we have is the 1/2 inside. And this explains why the formula has the 1/2, just halfway. Here we have y times y, which is y squared, but y is not allowed it. So I will write that as parentheses with f of x inside, and then square, and finally we have the dx. Ladies and gentlemen, x bar, y bar formula for you guys, right?